Hello everyone, let's go ahead and take a look at power series. And even in this case, we're going to be taking a look at whether a power series converges or diverges. Now, before we actually go ahead and take a look at how we can determine whether a power series converges or diverges, let's go ahead and find out exactly what we're going to be using power series for and how it's connected to the next section in our chapter. Now, what we're going to be doing is we're going to take a look at the transcendental functions, like say for example, all of our trig functions, our inverse trig functions, the logarithmic and the exponential functions, and we're going to try to rewrite them as an infinite, a polynomial of an infinite number of terms. Okay, a polynomial with an infinite number of terms, which is what we're going to be calling a power series. So we're going to try to take a transcendental function and change it into a polynomial with an infinite number of terms, which we're going to just be calling a power series. Okay, so now notice again that the one thing that's different about our power series from the other infinite series that we're taking a look at before is the presence, of course, of an independent variable x. Okay, so the question then is going to be this. If we have, say for example, a particular transcendental function, and we rewrite it in terms of a polynomial of an infinite number of terms, is that actually going to be equal? Okay, and that's going to be a very important question to ask. Now, another way that we can actually go ahead and rephrase that question is, will the power series actually converge onto the transcendental function? Okay? And what we will do is we will use the ratio test to check for that convergence. Okay, so kind of to wrap things up again, okay, let's just kind of look over that. We have transcendental functions that are going to be, hopefully be able to be rewritten as a polynomial with an infinite number of terms called power series, which is different from the previous infinite series that we're looking at because of the presence of an independent variable x. And then what we're going to do is we're going to use the ratio test to determine whether or not the power series is actually equal to the transcendental function. Okay, now when we actually go ahead and take a look at the convergence, there's going to be three different possibilities for what we're going to call the radius of convergence. And what I'm going to use there is the letter R, capital letter R. Now, again, what we're trying to do is using the ratio test to check to see whether or not this particular power series is actually equal or convergent onto the transcendental function f of x. And say, for example, if the only possibility of the convergence is when x is equal to a particular value of a. Now, if that situation actually occurs, what we're going to say then is that the radius of convergence is 0, because on the interval for x can only assume a particular value of a in order for you to actually have the transcendental function and the power series giving you the same exact value. So if that's the case, then we're going to say that the radius of convergence is actually equal to 0 because a point doesn't have any length. Now, let's say, for example, that for all values of x, the power series and the transcendental function is actually going to give you exactly the same value. Exactly the same value. And if that's the case, then we're going to say that the series converges for all x, x being an element of R, and therefore, being that R could be any number that we want it to be, the radius, x can be any number that we want it to be, the radius of convergence is actually going to be infinity. Now, let's say, for example, that there's only a particular interval for which the power series and the transcendental function actually give you the same exact value for a particular value of x. Then what we say is that for there exists in R is going to be a real number such that the series converges if the absolute value of x minus a is less than R, and it's going to diverge if the absolute value of x minus a is going to be greater than R. So again, notice that what we're doing here is we're going to be talking about a particular interval, and within that interval, the power series and the transcendental function is actually going to give you exactly the same values. Anywhere beyond that, it's not. It's going to diverge. There's going to be a difference between the value of the power series as well as the value given by your transcendental function for the same value of x. Okay, so before we actually go ahead and get more into the transcendental function part, we need to go ahead and be able to use the ratio test to check for our radius of convergence. And again, let's go ahead and see how that actually works. Now, if we go ahead and take a look at this particular power series here, notice again that the difference between all of the series that we've been dealing with before and the series that we're dealing now with, called the power series, is the presence of the independent variable x. So, what we have though, is we have a sub n is going to be x to the n divided by n factorial. And what we're going to do is we're going to use the ratio test. Let's go ahead and determine the convergence or divergence of that particular sequence. So I'm going to go ahead and take the limit as n approaches infinity. Notice that I have a sub n plus 1 here, divided by or multiplied by the reciprocal of a sub n. Notice that's in absolute value bars. And what I'm going to come out with after I do all the cancellations is that this is going to be equal to the limit as n approaches infinity of the absolute value of the absolute value of x divided by n plus 1. And if we take n to approach infinity, then what we know then is that this is also going to approach 0. Because what's happening here is that your denominator is going to be increasingly large and infinitely large, so that this would become 0. Now, based upon the results of the ratio test, we know that 0 is always going to be less than 1. So therefore, this particular power series is going to be convergent for all values of x, and therefore we can say that the radius of convergence is equal to infinity. Okay, let's go ahead and take a look at a couple of these other examples as well, so that we can see how some of these other results are also possible. Okay, so let's go ahead and take a look at another example here. Let's say, for example, we have the power series that looks like this, where we have -1 to the n minus 1, x to the 2n minus 1 divided by 2n minus 1. Okay, so again, what we're going to do is we're going to check for convergence using the ratio test. And I'm going to have a sub n plus 1 times it by the reciprocal of a sub n. And if I go through the simplification, basically what I'm going to be able to come out with is going to be 2n minus 1 divided by 2n plus 1 times it by x squared. Now, if I go ahead and take the limit as n approaches infinity, of course, this right here will just go to 1, because of course this is just going to be 2 over 2, which is 1. And so what that's going to be equal to then is going to be the absolute value of x squared. Well, the absolute value of x squared is just going to be x squared, because x squared is always going to be positive or 0. So we know it's just going to be equal to x squared. Now, based upon the results of the ratio test, we know that if it is to converge, this particular value here has to be less than 1. Now, what that means then is that we have -1 less than x is less than 1. Now, when we went ahead and talked about this part here, the possibilities for the radius of convergence, we talked about a particular, there exists an R, right, such that if the series converges, if this is true, and diverges if it is otherwise. Now, the thing is that it doesn't mention anything about what happens when you're actually talking about this particular radius of convergence, the endpoints here of -1 and 1. Could this actually be, could x actually be equal to -1? Could x be actually equal to 1? Now, what we need to do is we need to actually go ahead and take a look at those particular two values and then go ahead and determine whether or not it converges at those endpoints. Now, what's going to happen then is, like, say for example, if, let's use this one here. If x is going to be equal to 1, because that's one of our endpoints, then what happens then is that this power series, the x value becomes 1, which means that that is just going to disappear, because 1 to any power is 1. And it's just going to look like this. So notice that this is just one of our infinite series that we looked at before, and not a power series. So if I take a look at what we have here, well, that's just going to be an alternating series. If I use my alternating series test, I can check to see that it is actually monotonic decreasing, and I know that the limit of 1 over 2n minus 1 is actually going to go to 0. So I know that by the alternating series test, that's going to converge. Now, if I do the same thing to the left-hand side here, or the left endpoint, I should say, if x is going to be equal to negative 1, I come out with something up here as well, which is going to have a lot of negative 1 to something power. But again, when it comes to the alternating series test, I'm going to disregard that negative 1 to the power, and I'm just going to go ahead and take a look and make sure that I have 1 over 2n minus 1 fit the conditions for the alternating series test. And we know that it will. So what we have then is that this particular power series is going to converge also at the endpoints of negative 1 and 1, and so therefore the power series is going to converge onto that interval, and absolute value of x is less than or equal to 1. Okay, let's take a look at maybe one other example. Okay, and let's take a look at this last example here. Say, for example, if we have the power series, negative 1 raised to the n minus 1 times by x to the n divided by n. Again, using the ratio test, here's the absolute value of a sub n plus 1 times by the reciprocal of a sub n. And if I go ahead and take a look at what I'm left with after the cancellations, I have this. And of course, if I take the limit as n approaches infinity, this will approach 1, and so I come out with the absolute value of x. Now, in order for this power series to converge by the ratio test, we know that this result has to be less than 1. So I know then that negative 1 has to be less than x and has to be less than 1. But I need to now go ahead and determine whether or not the endpoints are convergent or not. So if I let x be equal to negative 1, then I come out with the infinite series that looks like negative 1 to the 2n minus 1 divided by n. Now, if we think about that, negative 1 to the 2n minus 1 is always going to be an odd value. And if that's the case, then you're always going to come out with a negative 1, which is this, which simplifies to this. Now, this, of course, is just going to be the opposite of the harmonic series, and we know for a fact that that's going to diverge. Now, on the other hand, if we let x be equal to 1, I'm coming out with this particular infinite series here, which we know by the alternating series test is going to be convergent. And therefore, we say that the power series is going to converge so long as we have x being less than or equal to 1 and greater than negative 1. Okay, so let's go ahead and kind of wrap things up again. We know that a power series is going to be different from our normal ordinary infinite series because of the presence of an independent variable x. What we're going to do in the end is try to see if we can take our transcendental functions and change it so that it looks like a power series, and then we need to go ahead and determine whether or not the power series converges to the transcendental function or whether or not they're equal. So what we'll do then is we'll use the ratio test to check for convergence. And we have 3 different possibilities for the radius of convergence based upon what the results of the ratio test is. And we know that it's going to converge at a single point, it's going to converge for all points, or it is going to converge on a particular interval. And when we come across that interval, we need to go ahead and check the endpoints to determine the convergence or divergence of the infinite series once that particular endpoint is given a value for x. Okay, so we'll go ahead and take a look at how we can notice that something is a power series, and also go ahead and use the ratio test to determine the radius of convergence. See you next time. Bye-bye.